Okay. Hey everyone, today what we're going to do is just run through some notes about vectors. We're going to try and keep this kind of as quick as we can, so we're going to hit all the points that we need to, and hopefully keep it within like a 40-minute class period's worth of time. If you really understood the summer assignment, then this might feel like kind of review. If not, like if you found yourself very lost in all of that vector stuff, then this is a good opportunity for you to, kind of just go over what it was that you saw there. We're going to split vector addition into two separate lessons, I think, for this. Today we're just going to do the first part. So, quickly, we're going to start out with adding vectors. As a quick recap, a vector is any quantity that has magnitude and direction. So, all right, that you should be familiar with. So anything that has a value and a particular direction associated with it. Now, the math that you do with vectors is different because it has direction. Basically, scalars are nice and simple. It's like 5 plus 4 is 9, and that's not so bad. But once you include direction, you have to sort of account for that when you do this. So how do we add vectors? We have to cover two different methods in this class. Vectors can be added graphically using what we call the tip to tail method. Some teachers will go over this as the parallelogram method, so if that's something you see like online, if you're trying to look up information, you might see it called that. So adding graphically basically means drawing a picture of what the resultant vector would look like, and that's what we're going to do for this lesson. For the next lesson, we'll add them up mathematically, so we're actually going to calculate something by using the component method. So that'll come next time. For now, just tip to tail method will be fine for us. So, some quick vocabulary before we move on. Resultant vectors. So we got to sort of get some of this out of the way before we really start talking about vectors. A resultant vector is the sum of two or more vectors. So basically, when you add up two numbers, you get a sum. When you add up two resultants, you get what we call a vector. The resultant of two vectors is also in itself a vector. So it also has a direction. And we'll talk about how we account for that in this lesson. So anytime I say resultant, it's the sum of two or more vectors. If you're trying to conceptualize like what it kind of means, a nice way of thinking about it is it's like the total effect of two vectors. Of two or more vectors, I should say. We're mostly only going to ever add two vectors, but you can do this for any amount of numbers. Because you can add any amount of numbers. And that's really just what we're doing today. So, just to get us used to this idea, and working with this a little bit. Mr. Evans tries moving a desk to the right with a force of 8 newtons. That's our unit for force. So, force is kind of like, I think, the easiest almost one to visualize or to think about. So I know we haven't covered force, but it's one I'm going to kind of use for the purpose of this lesson. So Mr. Evans tries moving a desk to the right with force of 8 newtons. And again, that just means the unit for force. A disgruntled student works against him by pushing to the left with a force of 5 newtons. So if we talk about how the direction is important here, we've got, so this would be me, Mr. Evans, pushing with 8 newtons. And then a student pushes to the left with 5 newtons. Okay, will the second student be working with Mr. Evans and make it larger, or against Mr. Evans, making it smaller? What do you think? And see, the answer to this one is, it'll make it smaller. These two forces are working against one another. It's like a tug of war. In a tug of war, the two sides pull against one another and kind of cancel out. Maybe they don't cancel out entirely, like would be the case here, but they are definitely working against one another, making each other smaller, I guess you could say. And the resultant, pause for a second and see if you can figure this one out. If we've got 8 pulling to the right, 5 to the left, I think the resultant should be 3 newtons. Now, resultants are also vectors. They have direction. So I'm going to go 3 newtons towards the left. Cool. Awesome. Now, The student and Mr. Evans settle their differences and work together to push the desk to the right with the same force values as before. In other words, we've got 8 to the right and we've got 5 to the right. Will the second student be working with Mr. Evans, making the force larger, or against Mr. Evans, making the force smaller? Well, if we're both in the same direction, then we're like combining, we're helping each other out, and so they'll combine to make a larger force. And in the same direction, they complement one another. 8 and 5 in the same direction would make a total of 13. 13 newtons to the right. And again, because they're both pulling to the right. Now, when we do vectors, and we've already covered this in class, when we do vectors, we talk about them using angles. That's how we define their direction. Now, two vectors will create their largest resultant when they're separated by blank degrees. And this one is going to be 0 degrees. Because when two vectors are separated by 0 degrees, they're pointing in the same direction. So we talked about the degrees already by doing like north of east, like south of west, and that whole thing. Here we're not necessarily talking about that. We're talking about how the two vectors compare with each other. So as an example, with the 8 and the 5, let's change color here. The 8 was to the right, that was the 8, and then the 5, let's go with a different color. The 5 was also to the right. Now, if you look at these two arrows that are right on top of each other, how many degrees could you squeeze in between these two? Like, how many degrees are they separated by? I would argue that they're separated by nothing. They're in the exact same direction. There is 0 separation, and that is why they're separated by 0 degrees. Now, the smallest possible resultant would occur when they are separated by, well, that would be opposite directions, right? So that would be like if you have let's go down here. 8 newtons pointing one way, and then the other one had a value of 5 newtons the other way. Now look at this angle in between them. What's the value of that angle? Well, I would say opposite directions, 180 degrees. Right, one's directly to the right, the other's directly to the left, like a semicircle around. And what this 180 degrees means is they are pointing in opposite directions. Now, it's important to point out that this is just the maximum and the minimum resultant. These aren't the only two options. Like if you have an object, like before it was a desk, let's say any heavy object, like a sled you're trying to pull or some furniture, just because you're pulling one way doesn't mean that your friend who's, in the same room as you has to pull directly with you or directly against you. They have other options too, right? They can pull at some sort of angle. Now, as they pull at these angles, we'll talk about how to get a number for those like in the next lesson. But for now, what I want you to understand is, as this angle gets larger and larger and larger, the resultant gets smaller and smaller and smaller. And the reason for that is when the angles are very close together, you see how these two are like mostly in the same direction? That means that they complement each other. They help each other out. If as that angle gets further apart, like this big wide angle here, are those two forces helping each other out? Not really, right? Because they're working against one another. So as the angle is closer to 0, that means the two vectors are more in the same direction, and the resultant will be larger. As that angle gets closer to 180 degrees, they're further apart. They're in opposite directions, and the resultant will get smaller. A little bit of practice with this idea. I'd like you to just pause the video for like a minute and try all of these questions, 2 through 5. I'll give you like a minute to try them on your own, and then I'm going to go over them. So take this second, pause it, and see what you can do. All right, I'm hoping you paused the video, gave this a shot. Let's try it out. Two forces, a 25 Newton force and a 15 Newton force, act concurrently on an object. Okay, I want to talk about this word for a second. That just means at the same time, like current things that are current are happening now, and that con prefix con means that together or with each other. It means at the same time because they're acting act on the same object at the same time. It does not reference direction, so this does not mean they're in the same direction. It does not mean they're in opposite directions. It means it could be in any direction. We don't know without more information. So 25 and a 15 Newton force act concurrently. Which of the following could possibly be the magnitude of the resultant? Two of these, and again, there's more than one correct answer here. Two of these I'm hoping popped out at you right away. Oops. And I'm hoping that those two were 40 newtons and 10 newtons. 40 newtons would be the two added together in the same direction, right? 25 plus 15 is 40. So that would be the maximum resultant, which again happens at 0 degrees when they're in the same direction. If they were in opposite directions, like 25 and 15, we call that 180 degrees, and that would be the minimum possible resultant. But there is a third correct answer choice here. And that third correct answer choice is 18 newtons. And I'm not going to hold you responsible for calculating the angle quite yet, but there's some angle in between 0, meaning right on top of each other, and 180, directly against one another. There's some angle in here where it'll be less than 40, greater than 10, and it'll be 18 somewhere in there. It can be anything in the middle. 40, 39, 38, there's anything all the way down to 10. 18 falls squarely within that range. You'll never have 25 and 15 add up to something more than 40 because they just can't make anything that big. They'll never add up to something smaller than 10 because they just can't make anything that small. But anything within this range can be made, at some strength, at some angle in between 0 and 180. So again, we have a maximum, a minimum, and then a whole range in the middle. Number 3, two forces act concurrently on the same object. As the angle between those two forces increases from 45 to 90, the magnitude of the resultant blanks. Here's how I want you to answer these questions. We're going from 45 degrees to 90 degrees. So we're taking two vectors that are separated by, I tried to do 45 degrees. And we're opening up the angle to 90 degrees. And the way I would typically do it is like this. If the maximum resultant occurs at 0 degrees, did we get further away from 0 or closer to 0? I think we got further away from 0, further away from the maximum. And moving away from the maximum would make the resultant smaller. Okay, 4, I just want you to understand what these angles mean. That's why I'm bringing them up. When two forces act on the same object, what does it mean for the two forces to be separated by 0 degrees? Basically, what that means is it's the same direction. And that when they act at this, separated by nothing, they will produce the maximum resultant. Conversely, if they're separated by 180 degrees, what that means is they're pulling in opposite directions. Like one is north, one is south, one is right, one is left. Something like that. And this produces the minimum possible resultant. Okay, I just really want you to understand what that angle means, what it represents. Okay, next up, equilibrant is just something I'm going to throw at you. It'll come up when we do forces, but for now it's just like here's a thing, and it'll come up later. That way the second time you see it, hopefully it'll make more sense. Equilibrant vector is a vector that cancels out the resultant. For now, if you can focus on that resultant, the equilibrant will come when we do forces, and I'll explain why it's helpful and why we would even care about such a thing. But for now, it cancels out the resultant. So, as an example, two forces act concurrently. Again, just means at the same time, does not mean anything about direction. A 12 Newton force acts towards the west, so every time I do these, I'm going to draw them out because I think it helps me picture what's going on. And a 5 Newton force acts to the east, 5 newtons. All right, what is the magnitude and direction of the resultant force? All right, well, 12 left, 5 right. Oh, it was west and east. Sorry, guys, I don't have a video editor, so all my mistakes are just going to be in here. 12 west, 5 east. Those are opposite directions, right? 180 degrees. So to find the resultant, we'll subtract them. They're going to take away from one another. 12 minus 5 is 7 newtons. And at 7 newtons, west, right? Because the west was the dominant force there. What is the magnitude and direction of the equilibrant force? Now again, this is just going to be something that cancels out that resultant. So if you wanted to cancel out 7 newtons west, what we would add to this is 7 newtons east, right? Because 7 west and 7 east would cancel out. In terms of what that actually represents or what it means that if I added another 7 going this way, you see how these would all cancel out? We've got 12 acting to the west, 12 acting to the east. The two sides are equal. This is the equilibrant, which is kind of a neat property when you talk about forces and accelerations. Yeah, for now, it's like we're talking about vectors. I'm just going to throw it in because it's relevant. Okay, so what we've done so far is we said that you can combine vectors. When they're in the same direction, we'll add them. When they're in opposite directions, we'll subtract them. Oh man, I should have fixed this guy, huh? Darn. So when they're in the same direction, we'll add them. When they're in opposite directions, we'll subtract them. And we call this the resultant, right, when you do that. But what if they're at some sort of funky angle to one another? Well, we can add them in one of 2 ways. Like we said on the first page, we can use the tip-to-tail method, which basically is drawing a picture to figure out what the resultant would look like. The next lesson, we'll take that tip-to-tail method and we're going to stick some numbers to it. So for today, we're going to draw a picture and we're just going to be happy with our picture and that'll be it. We'll add some math later on. So this is 2 vectors that we could add. Again, you can picture 2 forces. Here's a heavy object. One person's pulling this way, one person's pulling that way. If we call them A and B, A is pulling harder because they have a larger arrow, and B is pulling less hard in a different direction. Cool. Now these 2 forces, they're going to act concurrently on an object, which is represented by this dot right here. Use the tip-to-tail method to sketch the resultant force. So I'm going to go over the whole process and try and illustrate an example. But before we start, if these 2 vector arrows represent forces, like 2 people pulling the object, in which general direction would the object get pushed? So what I mean by that is, if you've got one vector, again, this way, one that way, what general, take a guess in your head right now. Which way do you think it'll get pushed? I'm hoping you're kind of thinking to yourself, I don't know, down the middle? Because this one's kind of that way, the one's kind of that way. It'll, find some way like that. So let's see if we can, create an answer using this process that, will match that idea or that guess. So I'm going to sort of try and illustrate the steps here. 3 steps, not so bad. First step. See if the vectors are, and this is where we get that name from, tip to tail. So first thing that we're going to do is check, because you might not have to do a lot of work. You might have to do an extra step in here. Now, when I say tip to tail, that means that the, I'll label my arrow parts here. The tip, which is like the arrowhead, touches the tail end of the other. So vectors that are drawn tip to tail are like the 2 that I drew over here. These are tip to tail. Because see how the tip of one arrow touches the tail of the other? Tip to tail. One after the other, like in a chain. Where one ends, the next one begins. That's our first step. It's just a quick check. So let's see if we can sort of replicate that by finding this resultant. Okay, are these 2 drawn tip to tail? I want you to think to yourself right now, are they drawn tip to tail? Yes or no? I'm hoping you said no, they're not. See how into the anatomy of an arrow here. See how the 2 tails are connected to one another? That means that they are not drawn tip to tail right now. Okay, and that's a problem, because this process is only going to work if they're drawn tip to tail. So what do we do about that? Well, step 2 is, if needed, and it's important, if needed, they might already be drawn tip to tail, then you don't have to do this. If needed, redraw one of the vectors. And when I say that, I mean redraw it so that they are tip to tail. Now, when you redraw a vector, just pick one. It doesn't matter. So, out of A or B, like, which one do you want to redraw? I'm going to redraw B, because, I don't know, that's the one I feel like redrawing. And what we're going to do is we're going to try and redraw it, like, perfectly. Like, if I could... I'm a terrible drawer, so I know this is going to go really bad. But if I could, like, take this exact perfect arrow and drag it... No, that didn't work. If I could take that exact perfect arrow and drag it across, that's what I want. Because remember, vectors have magnitude and direction. They have a certain length and a direction here. So I'm going to try and do it like perfectly. I'm going to... Oh, God. Yeah. Oh, that's not so bad. So, again, I just tried to exactly recreate this arrow. Exact same length. Exact same direction. Like up and towards the right. And that's what I was trying to redo. Awesome, and the reason this works is now we're tip to tail, right? See the tip of this arrow touching the tail of that one? They're like in a chain, one after the other. That means that we're finally ready to draw the resultant. So, that's actually exactly our last step. Draw, oh no, this handwriting. Draw the resultant. And the resultant always points from start to finish. If this sounds familiar from distance and displacement, or specifically displacement, it's because displacement is a vector. So we were actually doing this process the whole time. We just didn't sort of formalize it like this. So that's what I'm going to do. I'm going to draw it from start to finish. Just like displacements, it's often drawn with it's a dashed line, but it absolutely doesn't have to be. But it does need this arrowhead at the end. I'm actually going to do it in a different color so the arrowhead stands out a little bit better. Again, it does not have to be dashed at all if I ask for it on an assignment, and that's it, start to finish. And I think that roughly matches the guess that we had before, right? Before we said it would like kind of point like down the middle of the two arrows, like kind of like that way-ish. And this is, more or less matches that. So this works really well. And that's it. That's our process. Now quickly, I redrew vector B at the end of vector A. But what would happen if I did the opposite? Let's take a look here. So if I move B to the tip of A, then sketch the resultant. So I'm going to do it on this example down here. Notice we're doing the same thing, just in a different order. So B at the end of A is going to be kind of, long, directly horizontal, kind of like that. And then when I draw in the resultant, it looks something like this. Start to finish. I'm not going to dash it. I'll just call it R. Now, let's do the opposite. I'm going to move A to the end of B, right? Move A to the tip of B. So I'm just going to redraw A, but over here. Again, exact same length, exact same direction. And then I'm going to redraw that resultant from start to finish. Label it R. Okay, how do these two resultants compare? If I was any good at drawing, they would be exactly the same. Notice how they're both this like long to the right, kind of something like that. So does it matter which one you choose to redraw? Absolutely not. And if you looked at the example we just did, like let's say hypothetically I did redraw A. A goes kind of like this, right? So I'm going to go kind of like that. And you see how we all meet up and end at the same place? I mentioned earlier that some teachers teach this as the parallelogram method. And here I think you can see why, right? Because we end up with this sort of parallelogram shape. Down here you can see the parallelogram that would pop up if you redrew both of them. So if you want to actually just redraw both of them, just to like double check your work, that's okay. So how do the two compare? Again, I'm trying to prove the point that they're the same. This is addition. Addition is commutative, and it does not matter which order you do it in. Okay. Oh, no. So to close out, here's what I want you to do. Stop. Okay, I want you to do this page, do all of page 4. Pause the video right now, try it all on your own. All you're doing is you're using the tip to tail method to sketch the resultant. So you're just going to draw the picture for all of them. Pause it, try them all on your own. Again, you're just drawing, what is this, 1, 2, 3, 4, 5, 6, 7 pictures. Down here, this you might have trouble with the first time around, so we'll check our work at the end. Pause it, try these, and then I'm going to go over all of them once you pause and try them. Okay. I hope you paused it. I hope you tried it. Let's go. Here, let's call these vectors A and B. Let's pick one to redraw. I'm going to do A this time. Why not? These are not drawn tip to tail, so that's step one, is we're going to see if they're drawn tip to tail already. They are not. So I'm going to redraw A. Oh, God. Yeah, I tried there. On a test or quiz, it's okay if these aren't perfect. Most likely it would be multiple choice anyway. And then our resultant goes from start to finish. Nice, and that's it. So this one right here is the arrow that matters. If your resultant arrow looks like mine, you did awesome. Yeah. Okay, over here, just because it's a weirder shape doesn't mean that, this doesn't work here. So if we call them A and B, just for reference, I'm going to redraw B. It's to the right. It's kind of short. B. Awesome. Cool. And then we draw in our resultant from start. I'm not going to dash it because I feel like they turn out sloppier when I do that. Oh, God. Oh, this one was terrible. R, the resultant. So again, I don't care which one you redrew. You could have redrawn both of them if you wanted to. As long as your resultant looks like mine, you're in good shape. All right, let's redraw one, and then, so I redraw one. Oh, that was terrible. I'm going to do that one again. I'm going to redraw one of them, and then I'm going to go for my resultant, start to finish, R. Cool, that's it. So I was looking for an arrow directly to the right. Down here, I'm going to redraw the shorter one because it's easier. And then my resultant goes start to finish. Resultant. Awesome. Done. Down here, redraw one of them. And my resultant... Actually, I'm going to redraw both. Why not? Let's do it. Parallelogram method. Let's go. Resultant, start to finish. Okay, down here, doesn't matter which one you redraw. I'm going to do both of them again. Actually, I'm kind of into that right now. That one, and the resultant goes start to finish. So again, oops, I forgot to label this one. So again, for all of these, I don't really care which one you redrew, if you redrew one of them or both of them or the other one. That resultant, this arrow, should look, roughly similar to mine. I can't measure them because I'm not in school with a ruler, but should be similar. Down here, oh, come on. All right, last up. The last three I kind of expected you to have some trouble with, so let's spend some time on these. Okay, down here. This one almost kind of breaks the tip to tail. Here's what I'm going to do. I'm going to redraw the short one at the end of this one, but rather than redraw it right on top of it, which I find a little confusing, I'm just going to redraw it a little offset, like that. I know it should be right on top of it, but this is just easier for me to digest. Maybe it is for you. And now I'm going to draw on the resultant in pink. Then that resultant goes from start to finish. This is my resultant, R, pointing to the left, but a little smaller than the original. Here's a different way to think about that one. If you really didn't like that, I totally get it, because I probably wouldn't use tip to tail for that one either. If you think of it like this, big number to the left, let's call it, 12. Small number to the right, let's call it, 4. What result would they make? Well, 8 to the left, a smaller value to the left. And so actually, that's just kind of what I would do. I would say that the vector to the right just subtracts a little bit from the other one. This is exactly like a problem for displacement. Like, remember we did ones where it's like you go 12 west and then 4 east, and then your displacement would be like 8 west. It's exactly that. So if that made more sense to you, then that's literally what this is. Last up, sketch the equilibrium. All right, like I said before, I kind of expected you to get a little stumped here, so let's kind of walk through this one slowly. Remember, the equilibrium is something that cancels out the resultant. So let's draw the resultant first. I'm going to redraw one of the vectors. I'm a righty, so I'm finding these ones easier to do. Actually, I'm going to redraw both of them. Ugh. I tried. Okay. Now I'm going to draw in the resultant. Start to finish. That's my resultant. Now, here's what I want you to think about. We've got this arrow pointing upwards, right? It's got a certain length, whatever that length is. It's hard to measure on this PDF, but if I wanted to cancel that out, which way would I push or pull or point? Well, the opposite way, right? And I'd try to keep it the same length. I feel like these are kind of the same length. That's my equilibrium. Kind of what this equilibrium, again, When we do forces, we'll really talk about it. Kind of what this equilibrium means is if you took away everything, this equilibrium would cancel out the other two forces all on its own. Because it takes that resultant, the combined effect of the two, and cancels it out. So that's what it means. That's why we're doing it. So if you hate that for now, that's okay. It's a couple units down the road still. Over here, I'm going to redraw one. I'm going to draw in a resultant. I'm doing all sorts of colors today. Start to finish. So that's my resultant, which means that the equilibrium, and we're going to try and keep the same length and try and go exactly the opposite direction. The equilibrium. Okay, so that's our lesson for today. Quick recap of what we did. We did the tip to tail method. As long as you can redraw the vectors and draw the picture at the end, that's good. If you're able to do this and you're like, what am I actually doing? Why does this make sense? Why do I care? What's the point? When we add the math to it, I'm hoping that then you'll kind of see like, you know, why this works and what it is. So for now, I know it's kind of like, ugh, but, you know, the picture I think will become more clear as we go. We also talked about the angle between these, so the angle in between two resultants. We said that if you have like two given vectors, like, I don't know, 8 newtons and 5 newtons, they'll produce the maximum at 0 degrees apart because it's the same direction. And in the same direction, they'll combine and work together. They'll produce the minimum resultant at 180 degrees because that is the opposite direction. And the closer you are to 0, the larger the resultant will be. The closer you are to 180, the smaller the resultant will be. Because again, you're getting closer to that maximum or minimum value. That's it for today. We'll do some practice with this with the in-class worksheets and the quests and stuff like that. So you will get time to practice this. For now, we're just trying to save a class lesson day. And that's it. I don't know how to get out of this. How do I end my video? Oh, wow.